Okay, this week we'll move on for a little more about the atmosphere, kind of its origin, composition, and structure. So let's just see what else we can learn this week about some of the atmosphere. What's its composition is really a lot of it. And from that, its structure. So weather and climate issues, weather that happens in one part of the world actually impacts another part of the world. For example, dust storms that occur in the Saharas travel towards the west and actually impact the tropics and sometimes southeastern U.S. so badly that it may reduce visibilities to like 1 mile or less. So here is an example of literally dust storms in the Sahara impacting the United States. Dust can cause a lot of problems, obviously, as it comes across. And weather can change pretty quick. As we know, you just discussed a whole bunch of memorable weather events, but there's a lot of tranquil weather. However, sometimes it changes very quickly. So what is the Earth system? Well, it consists of the atmosphere, which is what we're going to talk about, but other things contribute to the atmosphere. The hydrosphere is water. So guess what? Water winds up in the atmosphere. Oh yeah, the geosphere, maybe volcanoes. Some of those volcanic gases can actually impact weather across the whole globe. And the biosphere is plants, and photosynthesis does play a role in what kind of weather may occur. Think about it. The atmosphere is pretty doggone thin. It really is composed of all these gases we're going to talk about, particulates in them. But within 32 kilometers or 20 miles, 99% of the atmosphere is there or below. Think about if you drove 20 miles down the road. Heck, if you ran a marathon, you could run the distance of the atmosphere. So it is not a very thick part of the Earth. The lower layer of the atmosphere is composed basically of nitrogen, oxygen, argon, carbon dioxide, water vapor, all part of that. Once you get above that, things change and they kind of get mixed up a little bit. And oxygen is the same if you were at the surface of the Earth or on top of a mountain. The percentage of oxygen is the same. However, the amount of air decreases. The number of air molecules decreases as you go up. So that's why you have trouble breathing the higher up you go, because even though the percentage of oxygen is the same, that amount is going to be less because the number of air molecules are less. And there are water vapor that basically can be up to 4% in the lowest 1 kilometer of the atmosphere. And carbon dioxide, it's required for photosynthesis. So it's really a good thing it exists. And it also keeps us lower from the greenhouse. Temperatures warmer from the greenhouse effect. So that is also important. Pollution is an issue. This is just a picture of smog at Los Angeles. It can be anywhere in the world that you have this. Some in China, some in other countries. It is just a fact that there is going to be pollution around. How much pollution can actually, too much is kind of bad for people. So the idea is to control it to an extent. The scientific method is used throughout meteorology. And I'm going to give you a quick example of one. Say I was interested in knowing what thunderstorms were going to come across the Appalachian Mountains from West Virginia into Virginia. It was a question that a lot of meteorologists have had because sometimes they come barreling through and you just wind up with all these strong thunderstorms that just keep rolling all the way to the coast. Other times they get the mountains and die, literally. They don't even make it across the mountains. So the question was, what caused that? So that was the question. Now we formed some hypotheses. Some of them included how the atmospheric stability, which we're going to talk about later, was. Maybe the wind direction, maybe the temperature amount of moisture. We took each one of those hypotheses and then analyzed results from our observations to see if that would actually support why these thunderstorms came across. And eventually we did come across the hypothesis that worked. And we were able to generate literally a simple number based on several atmospheric variables that would give us, okay, if it was greater than this number, the probabilities of these thunderstorms moving across the mountains and continuing were fairly high. If it was below that number, it was fairly low. This significantly impacted the forecast as you came east across Virginia and North Carolina. There are other studies of the atmosphere, like atmospheric vortex chambers, like they have at Purdue, that you can also have mathematical models. Everything we're going to talk about, while there's not much, very little math in this course, can be explained in atmospheric equations. We got to observe all of this weather. So how do we do that? Well, there's ASOS, which is an automated surface observing system. It's at almost every, well, it is at every major airport. And AWAS, which is another type of this system, maybe not as complex or as accurate, is at many of the, almost all of the smaller private airfields. There are very few airports now that do not have it. The reason it's at the airport, we want to know, if you're a pilot, you want to know what the weather is like as you're taking off and landing. So that's why all these observational equipment is there. All of this is automated. So there isn't a person looking out the window telling you what the weather is. And ASOS, for example, can give you every 30 seconds a new observation. That's how quickly the instruments are calibrated and take an observation. So that if you're a pilot coming in, as fast as the sky condition is changing, as fast as precipitation may begin, new observations can be had if they meet criteria. There are other networks, such as the Cooperative Observing Network. Every county in the United States has one of these stations. The idea being to look at their data about once a month, maybe once a week. They're used for long-term records, but we can, as a meteorologist for the National Weather Service, I can call these, all run by the National Weather Service, and literally get an observation for that day. They're taken once a day at 7 a.m. in the morning, typically in the East Coast, or 12Z. And then there's the community COCORAS data, which are all volunteers. If you want to volunteer, they'd love to have you. But they're asking you to enter precipitation, amount, and type, literally, each day. So how else do we observe? Well, we just talked about the atmosphere going up about 20 miles. I want to know what's going on in the whole atmosphere. I don't want to know just here where we live, down on the surface, because the whole atmosphere is going to impact what happens down here at the surface. So one of the instruments that's used is a radiosonde. Literally, we send it up on a balloon. It goes up to about 100,000 feet. The balloon keeps expanding because there's less and less air around it, and eventually breaks. Parachute comes out, and the instrument comes back down. Readings are taken as the instrument is rising, so that literally every minute as it's going up, there's a dew point, a temperature, pressure, and wind direction calculated. It gives you a vertical profile of all of that. Now, the other direction, especially in hurricanes, and if you're going to look at Hurricane Ida right now, there is almost continuously aircraft from the Air Force or NOAA going into that storm that are doing what we call drop sondes. And these drop sondes literally are dropped from an aircraft, maybe at 15,000 feet, maybe at 30,000 feet, down into the ocean. As they're going down, they collect exactly the same data as is collected from the radiosondes as they're going up. So the difference is the drop sondes are going down, the radiosonde is going up. Then we also look at radar. It's another means of remote sensing, and satellite data. And here is just a temperature profile in the atmosphere and how we divide it up. Notice in the troposphere here, where we live, everything, generally the temperature is going to be getting colder. Once you hit the stratosphere, it begins to get warmer. If I were to show you a vertical profile of the atmosphere from a Stuvie diagram, which you're going to be seeing in your labs with time, Temperatures, once you hit the you will see the tropopause because temperatures will begin to warm and continue to warm. Now, as you go up, once you get out of the stratosphere, in the mesosphere, temperatures beginning to cool. And when you get to the thermosphere, they go the other way. Auroras are just caused by a lot of solar wind. Solar wind is magnetic particles, plasma, all coming off the sun. The more of it that comes off, the better chance for auroras to impact further and further over the world. And here you can see that. And there are a few minor, like I say, here's the minor gases and all, and the different levels of the atmosphere. So now let's take a quick peek at just a couple things going on in the weather today, just to show you. For example, this is a loop, regular satellite loop, visual image, going on currently over the central part of the U.S., basically centered just a little bit to the west of West Virginia. And you can see here there's a whole line of clouds to the south of West Virginia, and you can actually watch them growing with time. There's a cold front up here and a warm front pushing north, and you can see clouds and thunderstorms developing there. This is a great tool for looking at how things are happening, because we don't have people giving us an observation from every location here. But by looking at this, I can see there's a lot of cumulus clouds here, and they're kind of expanding to the north, but there's a really biggest cum right along this line, and they seem to be moving northward with this. So if we were to look at the weather predictions, here's a surface front that north of that area. So it's interesting that there's a little feature here of some type that's causing these thunderstorms down to the south. Maybe not all that's showing up there. And this is a very high resolution. Looking in at that surface warm front, we know we have thunderstorms up here. Notice the temperatures to the south. Here's our 80s. Temperatures are always in the upper left-hand corner. Pressures in the upper right, which is 1019.8. Go across the front. Pressure is a little higher, 1020.3. Temperatures significantly cooler, 73. Oh yeah, the dew point is actually down at 70 here versus 73 here. Winds is from the east. Wind is from the south here. So you can see this define this warm front right here, a transition between warm air to the south, humid air to the south. And even though it's raining up here, the air is actually not as humid. But there's a very different types of weather up here. If you were north of the front, temperatures are in the 60s back in here, even some 50s. And south of it, temperatures are in the 80s. And if I wanted to go to West Virginia here, which I thought was kind of interesting, where those thunderstorms are developing, it's real hard to see, but right along here is kind of a wind shift. Not much of one, but that seems to be where the thunderstorms are developing. And so that little tiny feature has played a role in those thunderstorms. And here's a radar image up across Cleveland area, which actually shows some showers and thunderstorms up here to the north whenever it comes up here in a second. Yeah. While it's doing its thing. There we go. Yeah, you can see some new showers forming here, and you got some across north of that area here. So this is Cleveland's radar, depicting again some of the potential development of thunderstorms here. One of the things I did want to show, since Ida is going strong right now, is I want to just pick it out for you quickly. Here is Ida, south of Cuba, moving that direction, so it's going to go through this part of Cuba here in a little short time. This is infrared, so it's showing the coldest cloud tops. Right now, there is no eye, maybe a little tiny one, but I would argue there's not even that. But little tiny dot right there that might be the eye. So it's just developing, though. It's growing, getting colder, and the clouds are spinning around it. And once it gets into the Gulf of Mexico, it's going to have a lot of time to warm, very warm water. Be interesting to watch. So I hope you got some good information out of this. Please don't hesitate to ask if you have any questions.